Wind-assisted propulsion for big ships. You ready for this? Hello everybody, I am Nick the Naval Architect, and today I'm going to be reacting to a video that introduces the concept of wind-assisted propulsion by a startup company that's focused on this. We are trying to reduce the ecological impacts of large commercial freighters by outfitting them with a new type of sail-assisted technology. There are quite a few challenges involved, so let's see one solution that a company is proposing.
If we thought decarbonising cars was going to be challenging, how about trying to decarbonise something that has to transport 40,000 of them? Well, that is what the shipping industry is facing, an industry which represents 2 to 3% of the world's total emissions. Small challenge, this is definitely not. But what about if we started to harness resources that are clean, free, abundant, and we started using over 6,000 years ago? This is the Fully Charged Show.
So in the goal to decarbonize shipping, we're looking at a lot of alternative solutions. We are considering different forms of hydrogen fuel, ammonia, methanol, pure hydrogen as storage, but ultimately it always comes down to the fact that you need some new form of alternative power supplied to the vessel. And I love the fact that people are considering wind-assisted propulsion because all of the other technologies are pure invention. We've never done them before. There's a large learning curve. Whereas wind propulsion is something that shipping has been doing for literal centuries. We had a thriving global market of shipping long before we even invented the internal combustion engine. So I think we should still look at the other technologies, but I've always viewed that wind-assisted propulsion is the low-hanging fruit. It's the easiest technology to achieve and the one that we should focus on first.
And the thing is that cargo ships are all about economies of scale. The bigger the boat, the larger the cargo capacity, the smaller the shipping cost. And therein lies the challenge for wind-powered or wind-assisted technologies. It's difficult to make a boat of that size that's powered by the wind.
I would not say that the principal challenge is the sheer scale of things. Fuel costs for these vessels are so expensive. They contribute the majority of the operating costs of the vessel. Anything at all that you can ever do to reduce the fuel costs is most likely a worthwhile investment. The principal challenge that they're really facing, the majority of cargo ships in the world, whether they are container ships, bulk carriers, break bulk, all of these different options, they generally assume that we are going to be loading and unloading our cargo with cranes. Or at the very least, that we don't have to worry about any height restrictions or objects hitting us from overhead. You put a sail in there with all sorts of rigging and a giant mast, that severely restricts crane operations. And so now we're not only asking the ship to change, we're asking every single port in the world to change to accommodate some new method of offloading a ship. That's the major challenge that modern sails are facing, is whatever solution we come up with really needs to allow crane operations to continue as they are. We can't feasibly expect every port in the world to suddenly change their infrastructure. To get around the problem of cranes for loading and unloading, the first market that Sailbird is targeting is actually Roro vessels. These are one of the few vessels where we don't actually use cranes to load or unload the ship. Roro vessels stand for roll-on, roll-off, and that is where you have cargo such as vehicles, farm equipment, anything that rolls on tires. That type of vessel does not require a crane to get the cargo on and off, which makes it an ideal prospect for the very first sail-assisted propulsion.
Here is their 7.1 metre prototype, which they're using to figure out how to make this whole thing possible. So I have to admit, I expected something like Pirates of the Caribbean with, material sails. This is very different from this. This looks more like it's got 4 aeroplane wings vertically. How does this actually work?
Exactly as you said, it is the same as an airplane wing that we flip 90 degrees. One difference is that they are symmetric. On the airplane, since they only need to lift, they are asymmetric because then it's more efficient. We need to go in all directions.
So as you can imagine, the shape of the sail does a lot to determine how much force is generated by that sail. Traditional sails are just pieces of cloth that are held in an approximate shape. That's what you see on most modern yachts. We like that approach because it makes it very easy to fold the sail up, but it also is a very inefficient shape when it comes to extracting force from it. Most of the modern commercial sails are focusing on this foil style design where we are creating a three-dimensional sail shape.
How it works is that when we put a wing, a flat plate would work as well. In an airflow, the wind impacts it and it deflects. Because we put an angle to it, it deflects the wind and that generates a force.
But I guess the critical difference is that normally on an airplane wing, or actually even with a sailboat, you have one sail, maybe maximum two. There are four here. Presumably that makes it more than 4 times more complicated.
I don't know if it's 4 times, but it is definitely more complicated. With a normal sailboat, we would have normally a main sail and a small one in front. And they're very close. We know that they interact a lot, and that actually we know quite well how. But these have a very different shape and very different location, so they don't interact in the same way.
So one thing I find very interesting about this whole concept is we're saying 4 big sails is complicated. My background, I used to work with tall ships where I would actually sail them, and a traditional cargo trading tall ship, back before we invented engines, a traditional tall ship would have on the order of 27 or more sails. So saying that, we only have 4 sails, I don't really see that as super complicated. In fact, the whole reason that we shifted from those super complicated 27 sail plans down to your modern yacht that only has 1 or 2 sails really has to do with crew. The modern yacht only has 1 or 2 people on it, and so they wanted a design that allowed it to be managed with a minimum number of crew. We absolutely have the knowledge and the technology to create large, complicated sail plans, and the limitation mostly has to do with how many crew or how many pieces of automation technology you're going to need to manage that sail plan.
Fully automated wind-powered ships are a completely new field of research. So what exactly did the team need to do to map this uncharted territory?
What you're seeing right there is the internals of the model that they have, and that's pretty nice. I can tell you looking at that. They've got some nice machinery there. Good funding on their part. And that's awesome because that also means it's a very durable model. They can do a lot of research with that.
Wind is the obvious solution. It's always there. It's free. There is a lot of energy in there. That's the most logical way to use it, to go across the oceans.
They're not wrong. Wind is very much an obvious solution, but quite often in the marine industry, practical restrictions stop us from looking at the theoretical solution. From a theoretical standpoint, wind makes a lot of sense. From a practical standpoint, the major issues of how do we implement this without requiring everybody to throw away every little piece of marine infrastructure and start over from scratch. That's the really tough question of the practical side. Right now, no, you cannot put this style of a sail on a container ship because it's going to get in the way of the port cranes. There's a major practical challenge there in addition to the theoretical challenge. And so I think these guys really appreciate that challenge, which is why they are starting with the Roro vessels. Because first we need to show that the concept works. Then we're going to figure out the practical solutions of how to adapt that concept to other vessels.
Wind has been there for thousands of years, and I think it's been proven as a great way of moving ships forward. I think also wind has a lot of other great advantages. I mean, of course, it's free of charge. So with the concern now of oil prices and things like that, it makes the operating cost much less. And you should also remember that when you're now building a new ship, that means that you need to think of what will the fuel price be 2040, 2045, because that will have an impact on it. Wind, will be free. So that is a great...
Absolutely there. Fuel prices are not constant for ships. They do fluctuate quite a bit from year to year and even month to month. So you can buy a ship that required a huge investment on your part and was financially profitable back in, say, 2010. Fast forward 10 years now, suddenly the fuel prices have gone up too much, it's no longer profitable, but you're still stuck with this very expensive ship that you need to find a use for. That's a major concern. Pricing volatility makes it very difficult for companies to ensure they're profitable. Wind, just having that consistency is a huge advantage from a business standpoint.
The shipping industry is responsible for 2 to 3% of the world's CO2 emissions, which means if it was a country, it would have the same emissions as Germany. But it's also responsible for transporting 90% of global trade. That means 90% of the stuff that you can see around you right now, from food, clothes, electronics, cars, and all the materials that make them. So radically reducing or just stopping shipping isn't an option. We need both global trade and the solutions to decarbonise it. With the role of this prototype, I'm guessing, is to really understand the behaviour in different conditions.
The beauty of doing it in real condition that we don't control is that things happen that we wouldn't predict, and we get realistic conditions as well. It's going to be the same condition the real ship sails on, so the wind moves all the time. It changes in speed, it changes in direction. It can be very slow changes or very abrupt ones, and we get everything. So then we can really adapt the control algorithms to these real conditions.
How representative is this of what will be the 200-metre full-scale version?
Oh, that's a tricky question. It is still similar in how it looks will be similar. How it behaves to the wind changing, that's going to be similar. That gives us a lot of information about how the real ship would behave. We cannot just take that result and scale it up, but by comparing different ways of doing, we know which one would work better.
That is a tricky question. So there was a lot going on there talking about their scale model analysis. One of the challenges with doing a scale model like this is that your model is, say, 1/20th the size of the real ship, but your wind is not 1/20th the speed of the real ship, and it's not a straight one-to-one comparison. So you don't quite get the same speeds comparatively as you would at full scale. But as the video specified, a lot of their interest is not so much in the pure force from the sails, but in the control algorithms that the computer is using to adjust the angle of the sails. They want to make sure that that computer algorithm can react in the appropriate time and not overreact depending on what the sensors are saying. So in that sense, the case of using a live model is a very good solution. Practically speaking, it's also the only economic solution. They need months and months of testing. If they were to do that in an actual laboratory facility that can control the wind speed and match it to their scale, that would be most of their budget just to pay for the facility fees. So it's far better to use this real life model out in the open ocean and test it there. They also mentioned, how accurate is this to the final model? You'll notice their model doesn't include any of the complicated machinery to extend or unfold the sails. Their model was just a solid sail with a mast that they stuck into a socket in the model. So there's still quite a bit of structural and mechanical design to go from model to full scale. But as they said, that's going to come after they have the control algorithms. This is a very typical setup, as again, first prove that the basic concept will work, then go to a slightly larger version to find out what your new problems are and introduce the complexity of structure and mechanical. And you just incrementally go up like that, building on the parts that you know already work.
This all sounds wonderful, but what's the timeline for their first commercial voyage?
For 2024, we will put on the first wing on an existing vessel. So that will be in early 2024, and that means also that we can then optimize the system, really see how it behaves and how it's sailing in real conditions. And then for 2026, we will then have the large, fully sailing vessel in that way. So we see it as stepwise, that we move small steps in order to reach the big goal.
The year is 2050. Can we see Oceanbird crossing the Atlantic?
I hope most of the fleet will have wings, probably not just Ocean.
So one of the biggest questions that I have with the Oceanbird concept is the way that they're deploying their sails. They're using a cantilever mast design, which one of the biggest challenges with sails is how do you create a lightweight mast that can support all of that force? A cantilever mast is basically the most inefficient way to do it. It's just one really strong pull sticking up from the deck, which means that all of the bending, all of the strong forces are getting concentrated right into that location where the mast joins the deck. And in this case, right where that mast joins the deck, we also have the rotation joint to trim the sails to various wind angles, and we also have what looks to be a pivoting joint that allows the sails to lay down flat and go up vertical. So right where we need the sails to be the strongest, we're putting in two weak links that are now going to have to fight against the full force that those sails are producing. Can it be done? Yes, absolutely. You can make a machine that will do that. I do question about the weight that's going to result from that type of a machine, and I'm curious to see how they're going to integrate that in with the structure of the ship. That's going to be a major challenge as they bring this up to full scale.
The year is 2050. Can we see Oceanbird crossing the Atlantic?
I hope most of the fleet will have wings. Probably not just Oceanbird. Like, this one is going to be old by then, hopefully. In 2050, you will see a lot more of them. The challenges are to really make it happen, but I think we can actually do it. I'm very confident.
So this is a really good outlook for the marine industry. There will also be competitors that come up for different forms of wind-assisted propulsion, that Oceanbird will not be the only vessel out there. And that's very typically what happens, is you'll have a technology innovator like Oceanbird that does the hard work. They first prove that the concept can work. They generate the initial interest. And then the focus comes onto how do we refine that technology? How do we make it better? And once we get to that second round where we've had at least one refinement of trial and error, that's when you start to get widespread adoption where everybody wants to buy a piece of this. So it's really going to be interesting to see how Oceanbird is going to be breaking into that section, the type of response they're going to get, and the lessons learned to see how their own designs modify with trial and error and experience. It's going to be very cool to see what this turns into.
That will work. I think right now what's the most limiting is the will to do it. More ship owners and shipping companies need to be willing to do a change. And then the technology will be developed. I'm not scared of that.
And you should take in mind also that for the shipping industry, it's a quite conservative market. Vessels are lasting for a long time. So
when you're investing in an asset that has to last for 30 to 50 years, yes, you get very, very conservative. You start saying, oh, let's not rush. Let's wait another decade or two to see how things pan out. That's very much part of the shipping market. It is very conservative. And that's part of the tech challenge when you're innovating in the maritime area.
Everything that we do now will have an impact also in 2030, 2040. So it's important to start already now and also taking step by step.
Oceanbird have a long way to go, there is no doubt about it, and 2050 isn't that far away. We do not have time to just sit back and do nothing. But what is so encouraging is that a principle that has existed for so many years, since time began in wind power, is now finally being met by the technology and the appetite to bring it together to make some really sophisticated and commercially viable solutions, such that we could see wind power powering across the Atlantic Ocean, moving our goods.
Couldn't have said it better myself. I think it's very important to remember that sail technology, canvas and trees, timbers, was enough to propel our ships reliably enough around the entire world. Since those days, we have made a lot of advancements in science and building materials, and we can do a lot of things on a much more impressive scale now. So, yes, speaking as a designer, I agree that wind-assisted propulsion is definitely possible, but I'm not intimidated by the concept of 200-meter tall sails. That, to me, is a challenge, but an achievable one in the modern marine industry. And I'm also looking forward to see both what Oceanbird does and then alternative solutions that other people come up with. This is an open market where lots of people are trying to find the right mix, and we're all going to be learning from each other's trials and errors. So it's going to be really exciting to see what happens as this develops. Thanks very much. I'm Nick, the Naval Architect. You need an edge. Something to help your ship do more. DMS focuses on engineering solutions that will enable a small business to differentiate itself. So check out the website and learn how we can make your ship stand out from the crowd. Let's do something amazing. Thanks very much.